Points not.
Just drag it up.
It's nothing up there. It's just,
Oh, you got to see where it says pocket. There you go.
okay. Hi, everyone. Thank you for joining this seminar. It's our pleasure to have Dr. Chang here with us. He will have a talk with the title From PhD to Climate Entrepreneur, How to Fix the Planet Using Material Science. She has a PhD in physical chemistry from Harvard, also a master's in sustainable energy futures at Imperial College London, a master of philosophy in chemistry at the University of Cambridge, and a bachelor's of art in chemistry from Princeton. In the industrial work, she is a partner at Low Carbon Capital. Can go through the details here. She has been most recently a fellow at the Advanced Research Project Agency Energy, WPI, within the U.S. Department of Energy, where she developed new research directions for sustainable manufacturing of commodities. Prior to that, she has been the founder and CEO of the sustainable steel startup Average Engineering. In today's talk, she will discuss lessons from her chemistry research career studying sustainable technologies from solar photovoltaic to renewable fuel to clean metal production. She will also issue challenge to the audience, highlighting unsolved sustainability problems in the material science. It's a pleasure to have you, and the floor is all yours.
Thank you. So thanks to you. Let me screen share. I think we've managed to mostly figure this out, which seems pretty. Seems like we're mastering the hybrid world. All right. Looks like we're good. All right. That looks good, and that looks kind of okay over here too. And let me start my timer to make sure that we have some time at the end for questions. Thanks so much, everyone, for joining. I'll kind of do 3 parts: my journey in science, some open questions in material science and engineering that I think would be really exciting for y'all to solve, and then what I do now at Lower Carbon Capital. So to start off, I think the main lesson that I've learned from my time developing homogeneous catalysts at Princeton, and learning how you can patent something, but that doesn't make it go into the real world, to deciding to become more of an engineer and figure out how to apply what I loved about quantum chemistry and catalysis and electronic states to technologies, through a course at Imperial, kind of like a survey course, for ultimately then deciding to apply some of that broader knowledge that I developed in a photocatalytic solar to hydrogen system through a master's in chemistry at Cambridge. Also spent a little bit of time at Lawrence Berkeley National Lab using quantum dots as a way to make essentially smart windows. They were electrochromics. You change the voltage and that changes the coloration of the window. And through all these experiences, what I'd love to share to folks in the room who may be PhD students or postdocs is those experiences gave me an understanding of the clean and sustainable energy space. Back then we used to call it sustainable energy or clean energy. Now it's called climate tech because it's beyond just energy emissions, but also agricultural emissions and everything else that that contributes to greenhouse gases. But at least back in the day, that broader understanding of sustainable energy technologies really gave me a foundation and also a common language with which to speak with physicists, biologists, engineers, and sort of everybody in between. So if you're like me, and I think lucky enough to get excited about multiple technologies and living in multiple parts of the world, that would be my recommendation. Next, though, I basically pivoted, working on solar to hydrogen, so-called artificial photosynthesis. In some senses, a holy grail, turning like sunlight into fuels the way plants do, but can we do that better? Can we beat plants at their own game? And then basically, at least in my view, that dream a little bit started dissolving, because as it turns out, it was more efficient to optimize a solar to electricity system, photovoltaics, and then run that electricity down a wire and do electrocatalysis, right? An electrolyzer to turn water into hydrogen, a fuel. It was more efficient to do that than to do an all-in-one system, the sort of artificial leaf. It was a holy grail, but still hasn't really been proven out to be techno-economically more attractive than this two-step version where you can kind of optimize each thing for what it can do really well. So the writing was a little bit on the wall. It was 2014 and I wanted to start a PhD in something that was a little bit more close to commercial viability. And I decided to embark on a PhD in photovoltaics. That way I'd understand a little bit more how the market dynamic works and what the cost stack is, the levelized cost of producing solar, and make a chemistry contribution to make solar panels more efficient. And I guess that sort of starts my second lesson. So doing this at Harvard, I started in 2014, and you could sort of see the cost stack of utility scale solar, and imagine bringing that cost, that module cost down. That's that gray bar, because it was still sort of the plurality, if you will, the biggest cost piece driving, making solar still sort of too expensive for like massive adoption. And I think you guys see where this slide is. Where is this slide going? Like exponentially down, right? By the end of my PhD in 2020, we were really squeezed on those targets, right? Dollar per watt suddenly became not the target that we needed to be looking for anymore. And so I definitely had to do some introspection, and the lesson here is aim where the ball is heading, not just where the ball is right now. Hopefully a lesson that y'all can leapfrog. So again, like a time for reflection. We wanted to be innovating at the forefront of materials chemistry, and hoped that I would have a really long research career ahead. And so that pivot became an important time for me. It was the last year of my PhD. We were still patenting the solar stuff, and it was going okay, but like it wasn't going to change the world the way silicon already has. Because you can imagine this is going to keep coming down, right? And so feel free to fight me on any of this stuff also. Like if y'all are, if I was working on broad scale solar panels, if y'all are working on stuff that you think is gonna change what I'm talking about in any of these slides, like I'm super happy to hear it, because it's really about like moving our economy forward towards a sustainable version of everything that we do, like as fast as possible. So there, like no ego on ownership about being right about anything. So I'll say my moment led me to industrial decarbonization, because here in steel, cement, plastics were technologies where we didn't have one that was already cost effective, we didn't have a sustainable way to make things at scale that was cheaper than the incumbent, which is what we already had in solar generation. And so that led me to an interest in industrial decarbonization. And I came up with an idea, which I'll show you in a moment, around steel decarbonization. And so I founded a startup company based on this, although I just thought it was a proposal idea. Like, I just thought it was like, like, what am I going to do as a postdoc? What am I going to do next? And so you never know when you're an entrepreneur, and you don't even know it. So quick problem framing, and y'all are probably aware of this in much greater detail than I am from your classes. 5% of world greenhouse gas emissions come from iron making, and coal and natural gas, but largely coal is the source of that because you need carbon not only for properties in steel, of course, in carbon steels, but also it's used both for heating and then there are process emissions associated with the reduction of iron oxide to iron. So carbon is good, but these emissions are a huge problem. And current solutions, right, you could slap CCS onto a blast furnace, but that always adds cost. Like adding a component always adds cost. There are some other options too, like hydrogen direct reduced iron making, but the direct reduced means it stays in the solid form, so you're not able to melt out the gangue that is increasingly in today's ores that are just lower and lower quality, right? As time goes on, you like mine the pure stuff, and then what's left for the world to keep mining needs to be beneficiated. And for us to sort of appreciate where innovation can occur, I've broken this down to, I don't know, a quasi sort of spherical cow-like view of the world. And right, you take ore, you take out the iron oxide of the ore. This you may not need to sort of separate at this stage, in fact, but basic steps are you just got to like remove that oxygen and do this reduction to solid iron. Maybe you need to heat it, maybe you don't, in fact. And then we add carbon or other alloying elements to make usable steel products or mill products that are then of course fabricated into usable steel products. And what I'll note here is like there's no carbon emissions in this slide, like it's not like forcibly required of the thermodynamics of iron ore reduction. And so what we'd love is a technology set that has zero process emissions and also keeps emissions across the entire life cycle as low as possible, because you decrease emissions here in iron making that 5%, but then increase it somewhere else because of some like really energy intensive thing you have to do or coal intensive thing you have to do. That's not good either. So life cycle emissions are important to keep in mind. I'll sort of speed through this slide because I'll send these to you in case you're interested. Essentially, it shows, at least for the United States, that where all of the emissions and energy are associated with this process. Hopefully these numbers aren't in your quiz because that would be, I'll sort of do these too fast, but it basically shows that even in the United States, which is primarily, I think 2/3 of steelmaking in the United States is secondary steelmaking, is recycled steelmaking. Here, even still, the major emissions source in the US iron making and steel making value chain, there that 40 megatons CO2e is still iron making. So it's a problem here and globally. And here's kind of a simplified example equation of what I'm talking about in carbon thermic reduction. In my world as a solar innovator, I knew that every silicon solar panel that we install in 20 years, that's like a waste problem that we haven't figured out how to deal with yet. There's glass, there's aluminum in there, there's copper, and there's a decent amount of silicon. Not too much by weight, but because if you do mechanical crushing, you have P-type and N-type materials like all mixed together. You can't really reuse that in electronics or like, PV capacity. And so this silicon was sort of getting wasted, even as the glass and other stuff was being recycled. And that's a waste problem that's just going to sort of go up exponentially as like year on year we put in more and more silicon. So I sort of put my hands together with these two problems. And I said, well, silicon has like a ton of reducing equivalents in it, right? But yeah, it's just being wasted right now when it's end of life. And so that could be like a clean reducing equivalent. And then you're not making CO2 as a byproduct, you're making SiO2. So I developed like a small reactor and you heat this up to above melting temperature for the system. Also, it sort of has its own flux, like you're sort of essentially making like an essential component of a molten system here. And then the glass layer, you can either tap off or sort of let it crystallize on top. And then you're selling two products instead of CO2, you're making SiO2. So part one of lesson 3 is take big swings at big problems. The goal being like this is zero emissions, and gets closer to zero life cycle emissions. The pure iron you could sell at like a larger cost point. It seemed to make sense on paper, and I got money from the Harvard I Labs to start commercializing this and filed a patent and was pitching investors and went through NSF I-Corps. Happy to talk about this process. And I talked with the folks at BEV, and Dave Danielson said, here are the 5 big questions that I have about your technology, and take a hard look at it. This was sort of over the course of maybe 5 months, I finally got these questions. Happy to share them with you, but essentially, what is the cost? Which I already showed you kind of made sense. Is it compatible with existing steel production infrastructure, all of which more or less made sense because you just drop iron then into a steel making furnace, whether it's an EAF or a BOF. But this is where we had to fail fast. Like I could have spent years on this idea, but it wasn't going to make a huge impact on climate. Like I sort of went like this and said, yeah, there's like a ton of waste silicon coming down the pipeline, but compared to the scale of steel production, it's pretty minimal. And so as someone that decided sort of early on that I wanted to make an impact in climate, like this is what I say, 0.04% of greenhouse gas emissions, like that didn't feel like quite enough to really move the needle with one technology type. And yeah, you could have made a business out of this, but that's not what I wanted to be doing if it wasn't going to make a huge climate impact. And then similarly, the scale of the steel and glass industry don't match, which is not a huge problem necessarily, but just shows you how big the steel problem is, if anything. So lesson 3 is fail fast. Like it was important for me, I think, to go through this entrepreneurship process. And ultimately, I'm glad that I sort of didn't continue it further because as we find the hopefully the best uses of our time and talents, this experience showed me that these 5 questions you could ask them at the very beginning and maybe not spend five months on an idea that was going to fail here. And that's partially what I get to do now is like bring these types of 5 big questions to other folks who are developing new ideas. I knew I wanted to leave the lab bench and was interested in industrial decarbonization, but I was a bit at a crossroads and used my new kind of steel knowledge and basically said I want to spend a couple of years mapping the technologies in this space and finding the right reducing equivalent that like is actually highly scalable. And so I applied and was more or less accepted to a position at ARPA-E, which I'll tell you about in a second, but have this blank in my journey in science because I think it's important, or at least I found it important to sort of step back every once in a while and remember like, why are we doing this, and really meet folks that are impacted by climate change or will be impacted by the products that you'll ultimately be making. Like there's science that maybe turns into a technology, but then there's technology that turns into a product that's a thing that people are going to use, and who are those people that you're building for? And this is very informative because so I took a backpacking trip throughout Latin America doing sustainability sort of service work. And this was in the Huaro district in the highlands of Peru. This is where like the world's potatoes are grown. And this is Don Leoncio, and he is a potato farmer, and he's showing us our land. And he was like, yeah, of course we know about climate change. I mean, he didn't call it that, but he's like, yeah, every year potatoes have to be grown cold, they're in the highlands, and every year they move the potatoes like up to keep them at the right temperature, right? And it was just, really sobering to think at some point there's no more up. And in order to combat climate change, folks like Don Yoso and a lot of the folks that we stayed with are sort of combining traditional methods like rain dances with more modern methods like predicting the weather. But you know, I go back to this type of story and to Don Leoncio and what would be easy for him to use, like a fertilizer like method. Like he's not going to trust like a box with a bunch of like buttons, you know. And essentially design ethnography is a field that enables you to basically just interview people and ask questions. It's like a way to develop a really empathetic understanding of who your customer is going to be. And this sort of grounding has helped me figure out whether an idea is actually going to be used in the hands of someone, or if it's going to be too complicated or not really solving a pain point. Like we didn't go around asking them, would you use a device that keeps your potatoes colder? We asked them like, what is your day like? Like take me through a typical day for you. What does wellness mean to you? How did you make decisions about becoming a farmer versus going to the Amazon River like a lot of other folks, where it's just more lucrative, but then you're mining gold and it's also challenging. So I hope that this is, this was an important lesson for me, and finding your customer and developing a sense of who they are. Those are my 4 life lessons. They led me. I hope this has been helpful and primes y'all for questions. And maybe you can relate to some of these things. I'd like to, like I said, turn over to a second piece of this talk, which is a few challenges in material science that I see that would be fantastic if folks solved. And I think honestly, and many of these I mapped out in my 2-year position at WPI. Like DARPA, it's like a term limited position. So you have 2 years and then you have to leave. So didn't get to dig in enough on sort of many of these ideas. So as a caveat, you probably know the challenges way better than I, but here's the lens through which we think about things on the government side, which is to say, I don't know what the solution is going to be. Like the fabulously smart people in this room are who's going to develop those solutions. And it's not for us to say what that's going to exactly look like. But I could probably figure out, so here's page 1 for commodities. I could probably figure out what are sort of the bounding conditions, like the features of any viable solution would have to meet. And setting those out and then pressure testing them with folks. So if you disagree with any of these or the ones on the next slide too, like please let me know, because that's where where we get there faster. But if you sort of throw the gauntlet down with features of a solution, then maybe that can crack open the right answer, right? You're like, okay, well, it has to scale to 10% of the global market. Like, so for steel, for example, that would be the global primary market for steel is like 1.2 gigatons-ish. So 1,200 megatons. So maybe I could make one company that could make like a total of 100 megatons per year. And that would be pretty amazing. Well, what reducing equivalents are available such that stoichiometrically you could make iron from iron ore using that, right? You look at your Ellingham diagram, sort of look at like Kirk Optimer or Wikipedia, and like suddenly these bounding conditions like narrow you down to like a few reducing equivalents. It's not just one, but it's like probably not like 20. So I hope this is helpful. Happy to cover these a little bit, but essentially, so page 1, essentially if you're commodities, it's my view that you really need the levelized cost of this product to be parity with traditional manufacturing, because like whether you're making ethanol or steel or anything else, like these, materials, they don't have like a green sticker on them. They're just like molecules ultimately. And so they have to perform the same or better. They have to be at the same cost. These are replacement goods. And that creates like really stringent techno-economic requirements. I've mentioned ultra low emissions. And I think for iron and other process emissions technologies, you would also have to have basically zero process emissions. And I put that there because these are all commodities, they all have process emissions on the slide. And then handling the waste, like especially in a world where we're recognizing that like many populations have really been disadvantaged and are located right next to places where we're dumping our waste and like not taking care of it, right? Like the sustainable way that we make commodities in the future has to take into account environmental stewardship, otherwise it's not sustainable. Ultimately, this may mean just like a little bit more energy use to do like normal procedures to handle this waste, or it may mean innovative procedures. Either way, I think that's an important characteristic. In addition to iron, I'd be really interested in copper production, and while the scale of emissions is not as high for copper as for iron, nor is concomitantly, basically, we just don't make as much copper as iron. This is a critical mineral in my view, because the amount of build out that we're going to need of copper and other conductors for the grid is absolutely massive. And this is coming extremely quickly. But unfortunately, the way we make copper now, copper smelting is just like a pretty environmentally toxic method. So excited for folks to dig in and figure out a way to make copper that meets these requirements at the top. Zero emissions and zero waste. It's a bunch of like arsenic and sulfur, right, in these chalcopyrite deposits, and so a huge open challenge. I put another one on here that I don't know what the solution is for plastics. A way to think about it is you have end-of-life plastics. Either it's like a forever plastic, and many of those don't chemically degrade, but they physically degrade into smaller and smaller particles until you have microplastics, and that's just like in every dolphin's lungs, and that's not good. Or you have bioplastics, which you used to think about as sustainable, like that seems good, right? Bioplastics degrade chemically, maybe like bugs eat them or whatever, but they're becoming CO2, which means that at most, even if you're getting the feedstock for the plastic from like a bio source or like some CO2 source from the air, you're at most carbon neutral. But it would be, yeah, pretty impossible for it to be actually carbon neutral. Or worse, they're degrading this bioplastic into methane because it's an anoxic environment and it's in a landfill or something. Methane has a GWP that's like much worse than CO2. So these two stipulations, I haven't found what the solution is, but I'd be super excited for anybody to innovate around these two problems. Maybe it's a system solution, like come up with an alternative to plastic, like not sure exactly what it is, but we need it. The second quick page, beyond commodities, because these I lumped together for some of these categories, is around sort of more specialty equipment, or if I say specialty devices and chemicals, where maybe the cost can be a little bit higher, and maybe you can have a little bit of emissions because you're not making, gigatons of this stuff. Super briefly, and like let's go into details in other conversations. The technology still will need to be scalable. So you'll see superconductors as one of the examples. Like, great if you can make it at lab scale, but like, what is the technique that can also be made at like an industrial manufacturing scale? We may not be making gigatons, but we'll still need to make like tons to kilotons of this stuff, even if it's like a small component that enables like a huge change in clean energy. And scalability and techno-economics are related. Techno-economics, the levelized cost of this product. Some of these products are completely new, but they still need to be viable for the application. Okay. Often you can translate a technical property into, you can translate an economic outcome into what is the underlying technical property, such that if you solve that, the economic challenges will go away. So basically what I've said here is like, a holy grail is increasing the superconducting transition temperature so that you don't need like really advanced cooling systems. And when you take away the need for extraneous cooling systems, that will decrease costs. Another challenge with superconductors is processability. So these crystals, like you need to make them into tapes and wires so that they can actually be scaled in their use. Thermoelectrics were also still a ways away in the direction that I think is most exciting. So they'll transduce, of course, electricity and like a delta T, a delta temperature, but in the direction of electricity to delta T, which is what you'd really want for a thermoelectric or all solid state air conditioning, which honestly is kind of a climate resilience play these days. Like we're all going to need more air conditioning as the heat, as temperatures rise. ZT has been getting up there. Like there are some materials that have ZT 1, 2, 2.5 or so, all in the academic literature, but they don't yet meet the scalability and techno-economics considerations. So very excited for solutions here. I told Adam I was debating between putting permanent magnets that don't have rare earths at all, but still have extreme, like as good as performance as rare earth magnets. It's been a holy grail for a long time, and so in some sense can't not put it up here, but in some sense I swapped it out for what I originally had, which is rare earth extraction or rare earth oxide processing into rare earth metals that is cheaper to do because this separating like the lanthanides and the actinides and the lanthanides from the actinides ends up being really costly, like basically all the same with just like slight differences in solubility. And so the capex to like do these separations like multiple times to get sort of like small fractions in separation efficiency drives up the capital cost of this stuff and makes it harder to get access to these minerals. You have another one here. Yeah, this is a weird holy grail that's sort of arising as we double down potentially on nuclear fusion, in which you need to essentially like hold in a plasma that is, you know, the sun is able to do nuclear fusion, but we need to encapsulate this plasma so it doesn't go everywhere. What material can withstand 100 million degrees centigrade? Super interested in folks developing ideas. Liquid metal blankets, excuse me, sort of work because like a neutron will hit it, but then instead of damaging like a solid material, eventually like wearing away holes or whatever, the liquid can then sort of like reform over that hole. And so this is why these are potentially going to be used. In addition to these grand challenges, I'd be super happy to talk to you in this sort of next and third final section about what we do at Lower Carbon Capital and how we help folks that are interested in commercializing their technology go about doing that or seeing if it's the right idea, the right sort of path. I've been at Lower Carbon since April, and the first point to make is just like, we're in a climate emergency, but you are the people that are going to be able to change that. And once you do, you will also make a lot of money in the process. Like, you are the heroes of our generation. And these solutions are going to win, as I said, just because they're just cheaper and better than existing technologies, right? Like folks aren't necessarily buying Teslas because they care about the planet. They're still a little bit more expensive, by the way. So like not quite, they haven't quite hit the metric, but they're winning because they have the best like cost per range of any other EV and are basically providing like better features than existing internal combustion engine cars. And that's a good example of something that people are going to want in spite of any climate benefit. At Lower Carbon Capital, we're a venture capital firm. We invest in startups that are tackling three big things: slashing new emissions, so decarbonization, sucking up carbon, I'll say carbon, but it's really any greenhouse gas down from the atmosphere. So it's drawdown. And then three is buying more time. Buying more time for people and ecosystems that are on the front lines of climate change. This is a resilience and adaptation play, and is unfortunately becoming sort of increasingly urgent, say. Within slashing new emissions, we invest in everything under the sun, from electric production of cement to using enzymes instead of oil in order to do chemical production, to alternative proteins that don't emit the way they emit methane, the way cows do. We're investors in Commonwealth fusion systems, to other things that you might not have thought of sort of like climate technologies, but are, yeah, doubling down on how we're gonna green the grid, essentially. So basically everything, basically every sector that we have now, we have to do that, but sustainably. Under the second bucket, drawing greenhouse gases down from the atmosphere, there's any number of ways to do that, whether it's supercharged trees that are genetically engineered to draw down 2x or 4x the carbon that normal trees can. Hence, like a lot of it's being stored in the roots. This may sound crazy, but like dumping base into the ocean to, basically a lot of these sucking of carbon are like clever ways to either store CO2 as like CC bonds or carbonates, which is sort of a clever way of saying, how do we use clean methods to make base to like combine with CO2, acidic CO2, and create salt plus water, right? The third bucket, buying more time, kind of less material science-y, but it's everything from like putting sensors on electrical poles that can tell when like a tree branch is touching it to like send someone out there before there's like a fire event, to folks that are like predicting in microclimates like when there's going to be weather events to get people out of there in time. So as an academic, but now in venture, what I've seen beyond the technology working and meeting these kind of metrics that we talked about, the techno-economic metrics, there's kind of a holistic piece to what makes a technology ultimately a venture. And some of these we've seen before. So is the impact really large? Is it going to save billions of lives? And is the climate impact, on the order of, I don't know, 0.5 gigaton of CO2 saved per year? Humans emit 50 gigatons per year of CO2e. So this would be like 1%, which would be huge if you could draw down 1% of emissions. 2, can the economics be attractive? We already talked about. 3, like I said, know your customer. Is this going to solve something that is like a real pain point for them? Not just like a nice to have, like a vitamin, but a need to have. And 4, how is this? It may be a technology for all of y'all. It may be a technology, but it may be a new business model or a service. But how is this, whatever it is, this innovation going to be different from everything else that's out there? Again, it's kind of easier if it's a technology, because then you can either have IP around it, patents or trade secrets, either way, something that you're able to clearly be different than everybody else. What's the unfair advantage, and how will that continue over time? This one I called Get Off the Couch, which is just to say, is this team able to like have a good starting point, but then also pivot to better ideas every single time that they look at the problem a new way, And are yeah, like I said, are those ideas getting better over time? Because you don't have to have the perfect concept. I mean, right now, you're just kind of like, I don't know, what do I even want to work on? And that's totally cool. It's about that trajectory, because that also shows us like, you know, who you are as a person. And then, you know, similarly, is this team going to get shit done? Because like, I'll be really honest, like not all technologies are appropriate for a startup. Like many of them should be licensed or otherwise continue to develop to find sort of the right technology. And so a startup is like a particular path. It is really accelerated compared to what one normally does in the lab. So that's an important question to, you know, to be asking yourself, is this the right role for me? And honestly, working at a startup can give you a sense for that in order to understand whether that environment is what really fires you up. When you take venture capital money, it's because you want to move fast. You also have to sell equity for it though. So basically get grants as long as you possibly can, non-dilutive funding. But once you have to take venture capital money, sometimes it's $1 million if you're sort of quite early on. And then if that goes well, a second stage and then a third stage of funding, et cetera. So we play in the pre-seed, seed, and Series A stages. We have 1.5 billion under management. And so we have several companies that we've given like sort of this amount of money to. And venture capitalists kind of help you do all of the things around essentially the early stage of like what you're trying to do as a startup is take an idea for a business and as fast as you can experiment and figure out what is the right business model so that you can keep making revenue and you don't have to take venture money anymore. So it is an experimental search for a sustainable business model. And venture capitalists have helped many folks do that and sort of make the right connections and suggestions and essentially help that happen. So happy to talk about these things if you're interested. A lot of it in the really early stage is telling your story, helping with branding and figuring out why you're the right person and like helping you bring that story to the world. A few resources as folks are interested in like climate technology ideas. I love these books. Actually, number 2 on climate isn't a book. It is a great map of what's going to happen to the world if we do nothing. But it's very helpful. And yeah, I'll leave you with these. We'll send the deck around. But yeah, these books are really great. And once you're sort of situated, like the place to go really is to get data and more data and sort of really dig and figure out what is an actual climate problem. Here are some suggestions that will allow you to understand like every BTU of global energy use and how it's all tied together. Finally, yeah, I guess that's it. So I guess what I'll say is thank you for the opportunity to speak. I really think that the folks of this generation are uniquely capable of taking technologies that didn't exist 10 or 20 years ago and finally bringing those into the world in a sustainable way. So I hope you will join me on this journey and thank you so much for your time.
So my first great presentation, we open up the floor for questions. Both folks on Zoom and here.
We're opening it up for questions for folks on Zoom who didn't hear Maya say that. You're good.
All right, so anyone have questions?
Hey.
What are some of the companies and lower capital that you should on your roster?
Yeah, the question was like, what companies in lower carbon capital do I truly believe in? Oh man, there are loads. It's very cool. I'll try to keep this short. We're investors in a company called Lilac Solutions. They invented ion exchange beads that get lithium out of brines without essentially evaporating the whole pond, which is what you do today, more or less. I'm exaggerating a little bit, but the technology is very cool. They've raised like over $200 million, and we've sort of led many of their rounds and helped them pivot from like being a technology company to like acquiring brine sites in Chile, where you have to go down there and like read the newspapers to figure out like when the sales are of these salars. Yeah, it's taken PhDs into like a whole new level of like gritty deal making down in Chile, which has been really awesome for the team. A reason that I like Lilac is they're going after the lithium space. We're gonna need, I don't know, 4x more lithium than we make today annually or something like that for to achieve this electrification dream. So I think there's just a lot of tailwinds in their direction. And prices of lithium are kind of skyrocketing as a result of that, lithium carbonate equivalent. Even though they'll come back down, like this technology is profitable even when lithium prices come back down. Really believe in the team Zanskar has put together. They have PhDs in geophysics and are basically geologists, the two of them, the co-founders, CEO and CTO. And they had like a new drilling technology that was going to make it cheaper to do geothermal energy production. They were also playing around at the time with the idea essentially that the cost of geothermal production, the majority of that is in exploration. That is like you go, you dig this whole thing, and then there's like no hot water there, or hot, yeah, it's not hot there. And so huge amount of wasted capital has always meant that geothermal was just like never really in the money and never like the thing to really bet on. There are some, but you know, it's like the heat had been discovered because they were doing something else with the land already. And they're like, oh, great, a hot spring, and let's make geothermal here. So the unlock is prediction, figuring out which land is going to have these hot spots. And not only drilling, but Carl and Joel were developing sensing technology that was better than what was out there to figure out like, where is that needle in a haystack? So they went from being a technology company, which they sort of still are, to also just like basic, this is a lot like the Lilac story actually, like hiring companies to stealthily hire other companies so that nobody knew who was going to these auctions and buying this land that their like predictive data platform had figured out where like geothermal was likely to be. Because if everybody knows their technology works, then you're in an auction and just everybody's going to try to buy that land from you. And yeah, they're doing extremely well. It's the vision. It's kind of like a venture capitalist dream, right? It's like buy land for extremely cheap, prove that it's really valuable, flip it, move on. But they're also like PhD scientists and engineers, so they're not going to flip all of them. They're going to like drill and develop and like use their better technology to make geothermal. The reason I'm kind of doing this in reverse, I should say, like why we need geothermal is you need baseload power when as like a renewable energy source, and hopefully it's cheaper than nuclear, the only kind of other baseload power that we have yet. There are other ideas which are like still stealth, but are going to be awesome. Sorry, that was a long answer. Anyone else?
We have time for one more question. Yes, please.
Yeah. So, first of all, I love your energy on this topic. Really.
I'm keeping us awake here, guys.
Yeah, no, awesome. As we know.
Yeah.
85% of the startups fail
Yeah.
in the first couple of years.
Yeah.
Given your insights on each of the challenges of industries that
Mhm.
in terms of why haven't these problems been able to be solved before?
Yeah.
Where would you place your bet on
Sectorally?
sectorally, given that, hey, people need to make a living
Yes.
and a lot of researchers and students don't want to go down that route because obviously they gotta pay back their loans. So
Yes.
I'm just curious from your perspective.
Yes.
Where's the biggest opportunity balancing risk versus impact?
Yeah.
I would say.
Yeah, for folks on Zoom, the question was also really awesome. Which was like, hey, since startups are gonna fail, like, we want to choose sort of the best ideas and not just like do all ideas. So where would I, Christina, pick as sort of best optimum of like balanced risk versus sort of reward and impact? Perhaps unsurprisingly, I think critical minerals is highly important because like we see the tailwinds for electrifying the economy, and it's basically kind of like picks and shovels, right? So we know that in the gold rush, the folks that sold picks and shovels made more money than the actual rushers that were doing the digging. I guess I'm not trying to sound like mercenary about it, but I would not bet on any one mine, but I would bet that we're gonna need more lithium. I guess lithium doesn't really come from mines. It either, well, kind of, it either comes from spodumene, hard rock, or brines. But you get the idea, whether it's lithium, cobalt, nickel, rare earths, copper, we're going to need more. Demand is there, like demand is already there and it's going to continue to increase, whether that's customer pull, right? So folks that want to like buy green with their dollars, and that's translating to corporate pull. So corporates have made huge sustainability goals, and they're public and they're out there to keep their share prices up because people care about this stuff. Like folks want to know that they're working at a company that's doing something good for the planet. But these corporates don't have any idea how they're going to actually bring down those emissions to those goals. So I think a really easy way is, well, like we're at least getting our like energy from wind. But of course you need rare earths for those magnets, right? As an example. So I just think that's inputs to a clean energy economy, no matter where they're coming from, are really clear and are sort of the tools that we're gonna need. That's my guess. Thanks. What do you think? Do you agree with that, or was that total BS? You've seen this before.
Yeah, but no, to be honest with you, I've been out of the material science field.
Yeah,
for
sure.
a while, so yeah, I would actually look, I don't really have an opinion, I don't know enough about each of the industries to
Yes.
really make an opinion.
Yeah.
About that.
So yeah, that's sort of what we're seeing, so.
Look forward to talking to you later.
Yeah, absolutely. Thanks so much for coming. All right, Maya, thank you.
Of course, so we have a few minutes, I can ask a quick question, if you don't mind, is there among different industries, is there a specific one that you think needs to have like a major focus for decarbonization among, different industries?
Yeah, that's a great question. The question for the folks on Zoom was like, which field within decarbonization is really underappreciated, like hasn't been looked at enough? Yeah, I can think of ones that are receiving a ton of attention. New battery chemistry is an example, not to knock any of these, but it's just to say, like, as you guys in the audience are building your multi-year, multi-decade career, I would encourage you to run where the ball is heading, right? Not where it's already been, or like competing with technologies today. So, right, don't do what I did. I mean, my PhD was fine. You don't do a PhD to save the world, you do a PhD to learn how to be a scientist, but don't do what I did and like aim at dollar per watt peak and it's gone by you in like 5 years. So, so I guess my first like kind of cop-out answer is to turn that question back to you as you map out what you want your career to look like. But I think some examples are the challenges that I put on this slide. I think, oh man, what slide would it be on? I think all of these are neglected, every single one. And yeah, all of these are also neglected, every single one. I mean, it's like there are folks working on it that are doing really great, and I think we need more, as opposed to like an incremental researcher on perovskites. I hate to say that because I love perovskites, many of you do, I'm sure, these challenges are, I think, examples of where you can make a bigger impact, like a bigger delta of being a researcher on one of those.
Right. Yeah.
Thank you.
Okay, we are right on time, so we'll end this session. Thank you everyone for joining here and also in Zoom. And have a great day.
Thanks so much.